Thanks for that, Sid. Hi, my name is Elliott Hastings. I'm a PhD student here at Bristol in the Quantum Engineering Centre for Doctoral Training. Our research group, together with academic and industrial partners, have been developing systems for quantum key distribution with Cube satellites, like Sid said. My talk today will outline our progress in developing these systems, and in particular, I will discuss our field demonstrations of these systems. I'll start off with a brief comment on why satellite QKD is worth our attention. Channel loss is a dominant factor in determining the rate at which users can distribute cryptographic keys by QKD. It's well known that optical fiber typically induces 0.2 dB of attenuation per kilometer. This places an upper limit on the distance at which viable key rates are possible over fiber. However, satellite links enable quantum communication over global distance scales. For a recent example, the MISSIS satellite distributed keys between two ground stations 7,600 kilometers apart. This is possible because for satellite QKD, channel loss is independent of the distance between users. Instead, it depends on the link that each user can establish with the satellite. The advantage here is that atmospheric attenuation is negligible outside the lowest 20 kilometers. Signal loss is instead dominated by beam divergence, which increases quadratically with satellite to user distance. This is much more favorable than exponential attenuation in fiber. This picture shows a typical satellite QKD link, in which a quantum signal is exchanged from a satellite, between a satellite and a ground station. Optical beacons are often used for tracking, and RF signals are used for classical communications. Recent efforts have been concentrated on missions using cube satellites. These are a class of nanosatellite built from 10-centimeter unit cubes. Typically, CubeSats comprise 6, 8, or 12 units. Crucially, CubeSats are relatively inexpensive to research, develop, and launch due to their low size, weight, and power constraints. We are focusing on a downlink quantum channel in which a quantum signal is sent from a satellite to the ground. In particular, we are developing a QKD transmitter payload for a CubeSat and a portable receiver system to act as a ground station. First, I'll talk about our CubeSat payload. You can see on the right a model of the payload developed by our industrial partner, Craft Prospect. This will be mounted to the output of an onboard optical telescope. It is designed to transmit a QKD signal and a downlink beacon, and receive an uplink beacon, and it uses dichroic beam splitters to co-align all three beams. The uplink beacon will be impinged on a CMOS camera, which isn't shown here, and the centroid position of the beacon beam will feed back to a MEMS mirror. This will provide micro-radian scale fine pointing, which is well beyond the limits of the onboard ADCS. The sources for the transmitted beams are being developed at Bristol. The quantum source will use a BB84 protocol with 2 decoy states, and polarization encoding will provide resilience to atmospheric conditions. Basis choice will be asymmetrically weighted in order to increase our key rate. The downlink beacon source will distribute a De Broglie clock sequence to the ground station at a rate of 100 kilohertz. This is a cyclic sequence in which every possible bit string of some chosen length appears exactly once as a substring. QKD signals are sent at 100 megahertz, so beacon pulses are designed to be synchronous with every 1,000th QKD signal. The time tags of quantum signals between beacon pulses can be linearly interpolated. We are also developing an optical ground station, or OGS, to act as a receiver. This comprises a commercially available telescope on which the receiving optics have been mounted. When operational, multiple uplink beacons will be mounted to the telescope tube for so-called beacon diversity. In distributing the beacon over several beam paths, we are granted resilience to turbulence-induced pointing errors. The crucial feature of our ground station is its maneuverability. We plan to mobilize the OGS by loading it into a commercial panel van, though we can currently move it around using a pallet jack. Ideally, the OGS would be positioned in one of multiple candidate sites near a metropolitan area. As a result of being mobile, system operation can be made independent of local factors such as light pollution, geography, or weather at a given site. The CCD camera at the back is used to reorient when changing location by comparing pictures taken on-site to a star map. A mobile OGS will also enable surveys of candidate sites for larger static ground stations in the future. Other aspects have also been designed with operational flexibility in mind. The receiving optics are able to work with other satellite QKD missions with minimal realignment. The picture in the top right shows the receiving optics at the output of the OGS telescope. A dichroic beam splitter separates the downlink beacon from the QKD signal. These are the blue and dotted red lines, respectively. I've already mentioned that the downlink beacon is used to encode reference information. Similar to the CubeSat, pointing information is extracted from a CMOS beacon camera and fed back to a MEMS mirror for fine control. Timing information from an APD is used to decode the De Broglie clock sequence. A polarization analysis will be implemented in the near future, and this will drive motorized wave plates in the QKD beam path to correct for rotation of the satellite's reference frame. The QKD signal is then directed to a polarization detection module. This is pictured in the bottom right and uses beam splitters and static wave plates to passively choose one of 3 polarization bases in which to measure. The photons are then collected by fiber collimators and measured using single photon avalanche diodes. We are including measurements of the right and left circular polarization at the moment, but this is for information only, and it's not likely to be included in a final implementation. Importantly, only the dichroic beam splitter and filters are wavelength dependent. Changing these components will give our ground station flexibility to receive signals from different wavelength combinations. With this, we are able to integrate our OGS with other satellite QKD missions. Now, I've talked about several systems in isolation and how they should work together, but almost any experimentalist will agree that that's no guarantee they do work together. This is especially true when your experiment is in a dark, cold field and it's very late at night. I've included a picture of one of these cold fields on the right as proof, but hopefully there's plenty of background light pollution from nearby buildings. This means a vital next step is to test how these systems operate with each other and how well they work outside of lab conditions. In this way, we can develop a better understanding of and resilience to real-world factors, such as turbulence and background lighting conditions. For the first of these tests, we wheeled the telescope out to track some satellites. So here on the bottom, you can see a pass of one of the Starlink satellites. So we were able to track this with an accuracy of less than 1 milliradian using only TLE data. We are in the process of collecting more data for this, but we wanted to demonstrate we could at least do it once. We then moved on to integrating the transmitter sources with our receiver systems. It's been mentioned already that the downlink beacon source encodes a clock signal using De Broglie sequence, and this provides resilience to errors or interruptions in the free space link. This has been tested in the lab and shown on the left. The green stripes represent correct data, red shows errors, and the gray shows link interruptions. From the decoded result, it's clear that the source is able to operate in spite of these factors. Both the QKD source and the beacon clock source have been tested with the receiver systems mounted to the OGS and found to be functional. The barcode on the right is a section of data received by the timing APD. Finally, we are currently testing the subsystem conditions. To do this, we set up a free space link on campus. We've mounted transmitting optics to the side of the telescope and co-aligned it with the telescope bore site. We placed a mirror at a distance of 170 meters in front of a beautiful target and reflected some of the light back towards the telescope. The overall loss in the link was measured to be around 21 dB. Over this link, we have tested the beacon camera centroiding using wind as a handy source of mild turbulence. So the blue and green lines respectively trace out the Y and X pixel coordinate of the spot centroid over 33 seconds. With the pixel offset of 1.03 microradians, including magnification, a change by 4 pixels as seen in this data corresponds to an offset of about 4.12 microradians. In the near future, we hope to use this link to test the beacon and QKD sources. And in this way, we can demonstrate all of the subsystems required for free space QKD. From there, we can look into longer links and mobile targets. That's where I'll end the talk, but I wanted to quickly acknowledge our collaborators and funders. A special thanks to the team in Bristol, as this was a whistle-stop overview of their work as much as my own. Finally, thanks to the organizers, and thank you for listening. I don't know if there's any time for questions, but I'm happy to have final discussions in the chat or in the poster session. I'll be post number 19. Thank you very much.